Hello, my name's Melissa. I'm from 4512 West Torrance Robotics. We used to do FTC back in the day, but I think we are no longer an FTC team. I graduated in 2015 from West Torrance High School, and then I went to community college for a little bit, and then I transferred to UCLA, and then I graduated with a degree in math, and now I work as a software tester for General Motors, and I do a little bit of Java programming on the side.
Hi, I'm John Sauer. I did not do FTC, but I do have experience with FRC from 2013 to 2016. I'm a professional software developer, and I will be helping walk through some of the code examples.
So I wanted to add just a quick disclaimer. This tutorial assumes that you have basic proficiency in Java, and if you don't, I want to direct you to the W3 tutorial that they have. I highly recommend just kind of going through it step by step. I think all of it's really good. I would pretty much do all the Java tutorial, the Java methods, and then the classes, and then I would kind of stop at like inheritance and maybe polymorphism. I think just like everything up is really good and you'll use in FTC. I think everything after that, after inheritance, is really just stuff you learn in like your second year of college, and you don't really need to know that to do FTC. So this is definitely like a good place if you need like if you need to know how to do like if statements and everything else, and you're just like not sure what that is. So yes. So I kind of wanted to talk about the programming resources page, which is where I'm getting a lot of the material for this tutorial from. So if you want to get to this page, I would Google programming resources FTC, and this should be the first link. I also wanted to talk about like what this page has. It has like information for all the three options for programming, and then also like other useful links. You can kind of read through them and figure out what you need, and maybe this will be helpful for a starting point if you're trying to like maybe get into computer vision and object detection. So I wanted to talk about all the three options that you have when it comes to programming. You can program in blocks, or you can program in Java using OnBot or Android Studio. So blocks is what it sounds like. It's just grabbing and dropping blocks, and I would recommend this if you're just a complete beginner and you don't really want to get into programming, but you just want a functional robot. This is probably the way to go. I would recommend against it though, because you lose a lot of the functionality that you would have if you're programming in Java. So I would recommend either OnBot or Android Studio. OnBot is in the browser. Android Studio is an app that you would download onto your computer. So OnBot, I recommend this route if you have really good Wi-Fi wherever you're at, and then also if you're just limited to a Chromebook and you can't really download stuff because it's a school laptop maybe. So OnBot might be the way you want to go. Android Studio is what I'll be using, just because it's just the compiler has a lot more functionality. So I prefer this, and this tutorial is going to be continuing with Android Studio. But if you're between the two, I would recommend Android Studio, but OnBot if you can't really download anything. So without further ado, I kind of wanted to direct you to the Android Studio guide. If you're really getting started and have no idea what you're doing, they go over a lot of the hardware aspects of programming in the first couple sections of this guide, and then they kind of go over all the Android Studio stuff in the later half of this guide. And then what's nice about this is that they have links to everything. So in the Android, if you want to download Android Studio, this is the link. You would click this link, and then you would just kind of follow all the next couple instructions, and you should be able to download it pretty seamlessly. So this is the GitHub repo. It's a good starting place. And they talk about how to, if you need to download the project, well, you should download the project. You can either use Git or you can download the zip file, which you would just do here, and then you would unzip it using the extract all, and then you can figure out where you want to open the zip file. One thing I want to kind of point out is there's a whole wiki for this GitHub repository, and it's very good. So I would kind of click through if you're kind of getting started and you're not sure about a lot of things. It's very helpful. So one thing I also want to mention is the fact that there is a Java doc documentation. So all the classes that you use in Android Studio, well, in Java, have documentation for them. So you would find that in the Java doc. So if you're ever like, what functions can I use? This is how you would find out. So for example, so say I wanted to look at like the DC motor. So they kind of break it up. So notice how you have like robot core right here. You would just go to that, and then you would go to, oh, well, I passed it. Yeah, so it's DC motor right here, and it would tell you all the different methods right here. And so this is very helpful if you're like, if you kind of want to go beyond what's in the example code. This is kind of how you can expand your code. This is what the GitHub repository looks like when you've opened it up in Android Studio. There's a lot of example code and the external samples. So you would, to open that, you would do Java org first expires FTC robot controller external samples. And there's a ton of example code here. They have a bunch of like op modes and then some concept stuff. So basically, if you're like trying to get started with like TensorFlow or anything else, they have like example code for that, and they have a couple example code for like sensor stuff. So maybe you want to do like a color sensor or something like that. And then they have a couple examples for auto that might be useful.
So now we're going to go into code examples. So before we get started, I think one thing I should go through is generally a good order of operations that software teams should follow. So the very first thing you should be working on generally, once you have a robot that you can work on, is to work on your teleoperated mode. So the teleoperated mode is remote controlled. It's run from your joystick, from driver input, and you control your robot manually. Doing this first is good because it makes it easier to test. You can run different motors, have them mapped to buttons or whatever you need, and just generally make sure everything works. So like when you're working on the teleoperated mode, some big lessons that you'll get from this is one, just familiarity with all of the how you program the robot, understanding what all the different commands do, what all the different classes do, and also it will tell you how to control your own robot. So you can learn lessons like maybe what are the orders that all of your motors need to be going in, how fast do they need to be run, and so on, which is really helpful for just understanding your robot and making sure that you know how to make your robot perform the actions that it needs to do. Then the next step after that is to start working on your autonomous once you feel comfortable with your teleoperated mode. So big thing that you need to work on autonomous that will be newer is, rather than relying on driver inputs to control everything, you have to start utilizing sensors data, and you have to start building kind of more complicated sequences of events to control your robot. A big one that will be really new is actually controlling your drivetrain. So this will be using sensors like your encoders, using gyros, maybe using like bumper switches, just to kind of run through your sequence. And you're really getting that drivetrain path right is your first priority. It's probably going to be the hardest problem that you're going to have to solve. So once you have that solved, you can use all the lessons that you've learned from the teleoperated on controlling all of your actuators, your intakes, your shooters, your stackers, or whatever you're working on to complete your autonomous sequence to do what you need. Some other guidelines for the autonomous sequence: if you're a really new team, don't worry about all the stuff of like using all of these sensors and everything. A really, really, really easy thing you can do that will very reliably score you points is literally just to drive forward. In every FTC game, there's going to be some points in autonomous that are just done from driving forward or backwards. It's very easy. It doesn't require any sensors, and it's pretty much free points on the board. Another, even if you don't need that advice, some other good bits of advice would be, start simple and build off from there, because it's easier to have your autonomous mode, just do a short and simple sequence of events that can reliably score, and then once you feel comfortable, with completing that simple set, then you can work on building on that and adding more and more steps to score more and more points. Don't start by trying to do everything. It's really tricky to make an autonomous that's consistent, and you may be frustrated and you'll waste a lot of time trying to solve things that just can't be reliably replicated. So start simple, build from there, and if you're really new, just drive forward. Okay, so for this first example, we're going to walk through a very simple teleoperated mode. All this example is going to do is it's just going to take a drivetrain and have it be controlled by a joystick. Also, this example can serve as a really good template for building your own, because a lot of the classes and methods are all defined here, and you can just take this example and just start editing it as you see fit, rather than having to memorize how everything works and try to get it working right. Okay, so one other note is, a lot of the things I'm going to talk about are, they're in these comments for this example. So if you need some extra context or something, it may actually be in the comments here. So first thing you're going to do is you define just kind of some of your different member types. So your first thing you have here is an elapsed time object called runtime. That just tells you how much time has elapsed. It's just fed for telemetry. The next two things, left drive and right drive, are the left side of your drivetrain and the right side of your drivetrain. The type is DC motor because you're using a DC motor to drive them. So in a teleoperated mode, everything happens here. Is in your run op mode method. So in this example, the first thing you do is you add some telemetry, and then you go and define your left drive and right drive. So from here, you use this hardware map object, and you use these names here, left underscore drive and right underscore drive. These are defined using the FTC robot controller app. These are basically the names of the fields, and this is how you map a actual hardware circuit to your code. This next step here is to set the direction of your motors. So if you think about it on a drivetrain, let's say you're going forward, because they're facing opposite directions, to go the same way, they have to be turning opposite, think kind of like on a car or something. So in this case, the left drive is reversed and the right drive is forward. Now, of course, on your robot, it may be different. It really depends on how your robot's mechanically designed. Next thing you do is you wait for the game to start by pressing play, or from the field telling your robot to go in an actual competition. This can all just be copy and pasted into your code. And the next thing you should go into this while loop that runs just for as long as you're in teleoperated mode. So basically what's going to happen in this while loop, all of this code just runs over and over and over again. This is your main loop that you're going to have. So what you're going to do in the teleoperated mode for a drivetrain is you're going to take your inputs. So this would be from your gamepad 1, and you're going to look at your left stick Y. So basically this would be for going forward and backwards. So Y is kind of the vertical axis. And for turning, you're going to take the right stick on the x-axis, which is going to be left and right. So the way this would be controlled is the left drive stick just controls going forward and backward. Right stick controls going left and right. This is a very common control scheme for robots because it makes it so that each joystick control, one controls just what kind of how far forward or backwards, kind of your speed you're going, and the other one controls how you turn. So you can like drive forward without like going off to the side, and you can turn without moving. So this next thing you're going to do is you're going to actually combine those two inputs into the actual motor input. And one thing I should mention is on your gamepad and for your motors, they're going to be scaled from a range between -1 to 1, kind of on as a decimal floating point number. So this makes doing the math pretty simple because it's just -1 to 1. But it is worth noting when you look at the math here. So for your left power, it's going to be your drive plus your turn. So drive being your forwards and backwards input. And you're going to do what's called a clip operation, which is going to make sure that the sum of these must fit between -1 and 1, because you can't go over 100% power or 100% power in reverse. And you're going to do the same thing for your right power, except this time you're going to subtract your turn. Because if you think about it, if you're turning, you need some difference between your left and your right. But otherwise, it's the same calculation. Next thing you do is you're going to set the left power for the left drive and right drive for the right drive. And then the last thing you're going to do is you're going to put in telemetry for debugging or testing. I would recommend putting in telemetry even in your tele-operated code, because it can help you debug things, and it can be very useful for just making sure your robot is working the way it should. And if anything does go wrong, it can give you kind of an internal view as to what went wrong, so you don't have to speculate. So for this next example, we're going to work through a sample autonomous mode. Now, before we dive into the autonomous mode, I think it's worth talking about some of the sensors that are going to be used here. The two sensors that are for this are an encoder and a gyroscope, or I'll probably refer to them as a gyro. So an encoder measures how far a motor has turned. Literally, it measures, you'll see them sometimes called ticks or counts. But pretty much it just tells you, literally how much a motor has turned compared to when it started. These can be useful for navigation because you would put them on your drivetrain, and by tracking how your wheels move, you can have a good idea of where your robot is. The other one is a gyroscope, which measures, it looks at kind of the inertial forces to measure your rate of rotation. The principle that they work by is very similar to the way, in the human body, the way your inner ear works, that allows you to kind of like detect how you're moving even when your eyes are closed. This does, the same thing. One thing that you can do in a different example on here, it will just do autonomous that's purely by encoder, just purely by tracking the motion of your wheels. The problem with that is that it strictly, it assumes that your wheels are completely fixed to the floor. They don't skid at all, because if your wheels skid relative to the floor, then you no longer know where you are exactly, because you can't detect, how your wheels moved, what the robot didn't, just by the way, if you just all you know is how your wheels are. A gyroscope, however, because it looks at actually, its overall rotation, can tell you like, oh, your wheels have skipped or skidded on the floor. It would tell you that you still haven't angled yourself quite correctly. So I would recommend doing this. For just a purely encoder-based autonomous, it probably won't be all that consistent for anything except for very simple and short autonomous modes. Okay, so we're going to dive into the code here. The first thing we're going to walk through are the fields that this example uses. So the first two are your left drive and right drive, kind of like in the tele-operated example. These are the same thing. It's just the left side of your drivetrain and the right side of your drivetrain. There's a second thing here called your gyro, which is the sensor that measures your rotation. So here it uses the modern robotics I2C gyro. I'm not totally familiar with all the different gyro sensors that are out there, but the basic principle behind them is all going to be the same. It's also worth noting that the encoders for a DC motor are integrated in with the motor itself. All motors in FTC have encoders as part of as kind of part of the unit. However, that's an FTC thing. If you were to do FRC or just in the real world, motors do not have to have encoders. Motors and encoders are separate things. This next variable here, robot heading, is used to store where the robot is currently pointing using the gyro. The reason it has to use this is because the gyro sensor itself measures your rate of rotation. If anyone watching this has any background with a little bit of calculus, what it does is it integrates your rate of rotation to come up with your absolute direction or your orientation. Really, in simpler terms, all it's going to do is it's just going to add up your rate of rotation for every instant in time, and by tracking that, you can accumulate that into your actual heading. Okay, so these next things are some constants that are used to define how the robot moves. This first thing is counts per motor revolution. This counts per motor rev is 1440. So that tells you, that's a conversion factor that goes from encoder ticks or encoder counts to 1 motor revolution. So it takes 1440 counts for 1 revolution. It's a useful conversion factor. This next one here is your drive gear reduction, which in this case is 1.0, saying there's no gearing. This one entirely depends on your robot, how it's geared. You should talk to the people working on your drivetrain to understand what that is. Because if it's wrong, you're not going to calculate correctly where you are. This 1440 is specific to the Tetrix motor. Other motors may be different, and you should review the documentation to figure that out. But if you're using Tetrix, it will always be 1440. This next number is your wheel diameter in inches. Again, you have to know that because you have to convert, as you rotate, how far does your robot move? And that depends on your wheel diameter. So this next thing is counts per inch. So it's going to use all these together and do some math to calculate it. So first thing it's going to do is it's going to take your counts per motor revolution times your drive gear reduction, which will tell you basically how many counts per your wheel revolution. And then it's going to divide that by your wheel diameter times pi, which is this 3.1415. So that's going to tell you how many encoder counts are required per inch of motion on your robot on the floor. And what's nice about using these other constants up here is, by tweaking any of these, which are easy to kind of calculate or read up on, you can just pass it into this formula and it will come up with the right number. These next constants are some tuning parameters. So the first things here are your drive speed and turn speed. They're lower than 1 because generally drivetrains are going to be more accurate and more consistent when they move slower. So your drivetrain is moving at 70% power, and when you're just pivoting, you're going to be moving at half power. If you go full speed, it's very easy to overshoot, and it's also easier for your wheels to skid, which means that you're not going to be all that accurate. This next thing is your heading threshold. So what your heading threshold is basically saying here of being 1 is how many degrees do you need to be to say that you're close enough to being pointed in the right direction. So in this case, we're saying as long as we're within 1 degree, we're close enough. If you have it at 0, one of the problems that you can run into is, you have to be pointed exactly the right direction, which can be really hard to actually reach. It's a really tight margin. So what can end up happening is your robot gets deadlocked because it just can't move that last degree accurately enough to continue on, which is really unfortunate because time is short and time is precious. So you need to have, there's a bit of a trade-off between your tolerance for error and also your, desire to go quickly. So these next two are your P-turn coefficient and your P-drive coefficients. So these get into something that's called a PID controller, but really this is just called a P controller, which is a proportional term. So without worrying too much about what everything means, what this constant means is how much power should it put to your motor per unit of error. So in this case, your error is going to be in degrees. So what the 0.1 or 0.15 means is it's going to increase your motor power by 10% per degree of error. So that's kind of a tuning constant. There's, these values are not fixed. You have to tune them to what works for your robot. However, the numbers you see here of 0.1 and 0.15 are probably a pretty good starting guess. But like if kind of some ideas for tuning this. If it seems really slow, or if it gets close to turning all the way but then it stops, you need to increase this coefficient. On the other hand, if you find that it goes really quickly and it overshoots, or if it gets into some kind of situation where it just seems to want to oscillate back and forth around, around your target, then that means it's too aggressive, it's too powerful. You need to tune it down a little bit so that it doesn't overshoot and it just stops when it needs to. So that's kind of some ideas, but it is something that you're going to have to play around with to get exactly right. We'll return to these and put these in more context as we go on, but that's just kind of the quick overlook of how what all these fields mean. Okay, so we're back into our run op mode method, and we're going to start doing the same thing as we did in the tele-op mode. We're going to get our left drive and right drive from our hardware map, and then we're also going to set the directions the same way we did before. Our one's reverse and the other is going forward. The next thing we get is we're going to get our gyro object, which we get from from the gyro. It'll be named gyro or whatever you want to name it yourself in the FTC configuration app, and then we cast it to this Modern Robotics I2C gyro type. So that makes sure that you know that it's actually this object, and it will behave as that. So we're going to set our mode to stop and reset encoder. So what we're doing here is we're going to stop our motors and we're going to reset our encoder. So one thing to keep in mind, and I think it was mentioned earlier, is encoders measure relative to when they were started. They don't measure absolute rotation on your motor, they just count how far it's moved. So by resetting it, we're basically saying, reset the count to 0, just so everything's consistent and it's in a known state. So that's kind of what that does. Your motors stop and your encoder count is reset back to 0. Next thing you're going to do is you're going to calibrate your gyro. And the reason you have to calibrate a gyro is, remember that a gyro measures your rate of rotation. One of the things that can happen with a gyro, though, is that rate of rotation can be offset from the true number that it needs to be. So maybe if maybe you're stationary, but the gyro thinks maybe you're moving 1 degree per second clockwise. So when you calibrate it, what you're doing is you're telling the gyro that, hey, we're stopped right now, so whatever you're measuring on the sensor, make sure that is known as being, you're not rotating. So what we're going to do is the way this works is we call calibrate, and then we wait for the calibration sequence to finish running, and all we do is we just wait. So that's what the sleep and idle command is. We just tell the robot to do nothing. So this is going to be run when you initialize the robot, so when you turn it on. You're not going to be running this during a match. This will be done before the match, but it's important to have, and it's important when you calibrate the robot, that the robot is completely stationary, because it needs to, the gyro needs to know what, being still feels like, essentially. So then next thing we do is we're going to update our mode to run using encoder, which means that it's going to run to a set position on your motor. So you're going to run up to a particular count. Then we do, add some more telemetry. Then we reset our gyro. This is kind of similar where, again, you integrate or count how far the gyro has moved. It's very similar to what we were doing with the encoder, where we have to tell it where 0 is. And basically what you're going to assume is 0 is a direction, 0 degrees heading is the direction that you're pointed. So when you're running in autonomous mode, you assume that 0 is, where you start. And then you call get heading, which is going to update this robot heading variable, and we're going to walk through this function. It's towards the bottom of this file. So way down here, all you do is you just call get integrated z value, and z is one of your coordinate axes, z is up and down. So basically, as you rotate about your up and down axis, your vertical axis, that tells you how you're rotating. If you think about it, your robot rotates about a vertical axis. It doesn't rotate horizontally, kind of like a plane would. It's just steering. So that's why you use this z value as opposed to your x or y. But that's all this get heading value does, or this get heading method does. So when you see it used, just know that it's really just calling this get integrated z value. So back up to where we were, down a little bit. Up more. Okay, so next thing we're going to do is we're going to run through our actual autonomous sequence. So what we're going to do, oh, and also I forgot to mention, up here is while op mode is in it, all we're going to do is we just log telemetry and we wait for autonomous mode to start. So everything here and above happens just when you turn the robot on. Everything down here happens once autonomous mode starts. So this reset z-axis integrator and get heading happens the instant autonomous mode starts. So you reset your heading back to 0 then. So then you run through your sequence, and there's two methods here, which are gyro drive and gyro turn. So what gyro drive does is it's going to drive straight at a particular heading. So in this case, like, you're going to drive forward at an angle of 0. So just drive forward 48 inches at the heading that you start, which is 0. This next method is gyro turn, which will turn your robot about a point to the specified heading. So in this case, it's going to drive to minus 45 degrees heading. And it's worth noting that on these angles, and we'll get to this in a second, but the angles on your gyro are going to go from minus 180 to 180. The reason it does that is because there are 360 degrees in the circle, and 0 makes for a nice midpoint, especially if that's where your robot starts. So that's kind of the rationale for that. And then the rest of this is, and then the next function is gyro hold, which just has your robot stop and hold a particular heading, but not move. And then it's going to rerun through the sequence, which could be, you can tune this to whatever the game is, but this is just an example. And then we, tell it that it's done, and we, if this were a real match, we would move on to tele-op. Or if you're testing, you would stop. So we're going to walk through each of these methods here for gyro drive, gyro turn, and gyro hold. So the first method that we're going to be implementing here is gyro drive. It takes 3 parameters, which first one is speed, which is on a scale of 0 to 1, how fast you want or really the amount of power that you're going to be putting into your motors. Next parameter here is distance, which is how far you want to move in inches. Last parameter here is angle, which is the heading that you want to hold. And I think, as I mentioned earlier, all the gyro drive does is it's going to make you drive forward holding a particular angle and driving at a particular speed. So first we do is we're going to define our fields, which I'll cover as we kind of go through this. And then we check to make sure that we're actually in autonomous mode using this op mode is active method. Next thing we do is we're going to calculate how many encoder counts we need to move using our distance in inches times how many counts per inch. And what we're going to do is we're going to set our encoder targets as our current position plus how far we want to move. And then we're going to set our target to these target positions that we calculated before. And then we're going to set our run mode, which is run to position, which is just going to tell the motor controller to keep running until it's at the position that we've set it to. So what we're going to do for our speed is, one, we're going to just do some, I know I said that the range is between 0 to 1, but this actually ensures that it meets between them by taking the absolute value of your speed. So let's say you put in minus 0.6, it's going to be 0.6, and then it clips it to be between 0 and 1. And we go and set the power to left and right to be these speeds. And this will start our motor to start going in the direction that we need. So now what we're going to do is we're going to do a closed loop that's going to actually drive and hold our angles. We're going to walk through this here. This part gets a little bit, this is actually walking through the P controller. So the first thing we have to come up with for our P controller is we have to come up with our error. So we're going to go down here and we're going to return back to this line on 221 to get our error. So our error, there's two parts of this. You have to have a current value and a target. So all that your error is it's, in the most general term, it's your target minus your current value. So you can see here it's your target angle minus get heading, which is getting your gyro z-axis value. Now in this one, what we're going to do is we do have to clip our error, because if you think about it, a gyro goes in a circle. It's going to go from, it's on a range of minus 180 to 180 is where we want it. So what we're going to do is we're actually going to clip it. So let's say like you have a robot, you have a heading of, or you have an error of like 181, and your target is, if you have a current value of say 179, but your target value is minus 179, it might look like your error is 358 degrees, but really that's just 2 degrees. So that's kind of what this code is doing, is it's kind of shifting your value until it's in that range, which will help to correct for that fact that it kind of loops back around on itself for a gyro. For other types of sensors, like say for like if you're trying to set like a flywheel speed or something, you wouldn't be doing this, but this is specific to using a gyro. So we're going to return back to where we were for our gyro drive, which is our get error. So again, get error just tells us how far off we are from where we want to be. And our angle that we pass in from our parameter is the heading that we want to have. So it's going to tell you how far off are we. And so the next thing is we get our steering parameter, which we use our error and our P drive coefficient. The reason we're using our P drive is because we're in our gyro drive mode. So for get steer, this one is again quite simple. So if you keep in mind, a P controller is just a proportion. So it's our error times our P coefficient, and then we clip it between -1 to 1, because your motors can't output anything beyond 100% power. So that's just why we clip it. But at its simplest, it's just your error times your P coefficient. So returning back to where we were, we have our error, we calculate our steer, which is just going to be our error times our P coefficient. This next thing we do is we do need to actually invert our controls if we're driving backwards. So driving backwards would be if distance is less than 0. And then what we're going to do is we're going to set our left speed and our right speed where they're going to be offset by the steer value. So it's going to be the speed that we want to go. For left, it's going to be our speed minus our steer, and for right, it's going to be our speed plus our steer. Because basically you want to apply some difference to your drivetrain to help correct for that error. Again, a lot of this depends on whether it's a plus or a minus. Really depends on the way your drivetrain's built. If you're offset and it seems to want to keep leaning into its error and getting more and more wrong, you probably have these signs flipped. So rather than being speed minus steer, you might need speed plus steer, and vice versa. This next step here is to normalize our speed. So the reason we have to do this is, again, you can't output more than 100% power. So first thing we do is we get the maximum speed that we're having. It's going to be our left speed and the absolute value of our left speed and our right speed. And if either one of these is greater than 1, which could happen, like let's say our speed was 90% and then our steer was even more than that, we need to keep that difference, because if you still don't have that difference, you're not going to be correcting for it. So we divide by our max, which helps to ensure that even if one of our values is way beyond 100% power, we're still going to be steering, and it's still going to be on that -1 to 1 scale. So we just apply these powers, and then we log a bunch of telemetry. And all of this is going to run in a loop over and over and over again until basically, we're at our target point. So this is what this is busy. Left drive is busy and right drive is busy. And when they're no longer busy, we're saying that we're at our position. But the speed that it's running at is controlled by this P controller that's ensures that we hold the heading that we need. And then once that's all done, once we've made it to the point where where it's at the end position, we stop the drivetrain and we go back to run using encoder as our drivetrain. So we're no longer in run to position mode. So if you need to use your drivetrain for other things, you can do that. So that's the gyro drive. Now we're going to move on to the gyro turn, which is going to use a very similar principle in the P controller as gyro drive. Although I'm going to run through it again just for repetition, because I know that's especially if you're a newer programmer and you haven't done this can be quite confusing. Okay, so for gyro turn, it's going to be quite simple. So all we're going to do is we're going to, make sure that we're running, or make sure that we're in our autonomous mode, and then we check to see if we're actually on the heading, for our speed. So what on heading does, we're going to go down this, is it's going to return true once we're there, once we're at the angle that we need, and it's going to return false when we're not on the heading. But it's going to control our it's going to control kind of our motors and make sure that we're going towards the right heading. So on heading is the next thing. That's again going to run this whole P controller. So it takes a speed, an angle, and a P coefficient. So your speed is how fast you want to be turning. This would be your turn speed at 0.5. Your angle is the heading that which you want to start pointing to, and your P coefficient is the P coefficient you pass in. So as in the previous P controller, we get our error using the same method as we used before. Well, I won't go through it again. And then next thing we check here is we check our heading threshold. Remember that thing that was at 1? We need to, that helps us kind of that threshold to make sure if we're actually pointing the right direction. So when we're there, we tell the robot to stop steering and stop our motors using, so we set everything to 0, and then we say that we're on our target because we're saying we're done, we're pointing in the right direction. If we're not, we're going to call this get steer as we did before, and our right speed is going to be our speed times our steer, and our left speed is going to be the opposite of our right speed because we're turning, so we want them to be going, our wheels to be going in opposite directions. So we're just turning about a point. As before, the signs of these, like right speed being positive and left speed being negative, that kind of depends on the orientation of your gyro, or it depends on how the way your motors are oriented. If you seem to like if you want to point to a direction and your robot goes in the wrong direction, like if you need to turn clockwise to point the right way and it goes counterclockwise, you probably need to flip the signs on these. But it is important to keep these opposite of each other, because if they're not opposite, your robot's just going to go in a straight line. So what we're going to do is we set the power to both of our drivetrain sides, and we log telemetry, and we return whether or not we're on our target. So it's going to be true if we're within our heading threshold, and it's going to be false otherwise. So returning back to here, too far up, all we're going to do is this while loop, just make sure this keeps on this until we are pointed in the right direction. So this exclamation point means not. So for as long as we're not on our heading, we're just going to keep running this loop. So that's all the gyro turn does. It just, at a set speed, points you at the right way. So then our last method is gyro hold, which will hold a particular heading for a set amount of time. So in this case, it's going to be hold minus 45 for half a second. The reason we do this is to help the robot settle into our new orientation. If you were to start driving right after you started pointing in a particular direction, if your robot hasn't totally stopped yet because it has inertia or something, you might it might just start running off in the wrong direction, and it won't be able to control. And it can do it in ways that are very inconsistent because it depends on how fast your robot's moving once that happens. So holding helps to kind of smooth all of that out. So we're going to go to that, and it is going to work really similarly to kind of our. It's going to work kind of like our turning, where we're just holding. So first thing we do is we get an elapsed time. Then we reset it, so it's back at 0. And then basically we wait until our hold time is at 0, and we're going to call this onHeading method. In this case, we don't care if it's pointed in the right direction or not, because what we care about is this timer. It just needs to hold it for as long as it needs to hold it. And then once it's done, it stops the drivetrain and goes back. So gyro hold and gyro turn work very similarly. The main difference is the threshold, or is the condition to end this method. So for gyro turn, the condition is it's pointed in the right direction. For gyro hold, the condition is enough time has elapsed based on this hold time parameter. So going all the way back up here, that explains all these three methods. And at the very end, we just add some more telemetry. We sleep for a little bit, and then we go into teleoperate mode. So that's a really simple. I know this isn't very simple, but this is kind of a good introduction to how you would be, driving around the field autonomously, and how you would kind of build the sequence to do what you need. Now, obviously, these variables really depends on what you're doing, and it really depends on the game, it depends on your robot, and you're going to have to play around with the values on these to figure out what works. But when you have things like using distances and angles, it should get a lot easier to reason about what you need to do to make your robot perform the correct sequence. And also it'll be it'll be able to correct for minor differences. Maybe if the field, different fields may have different, maybe may have more or less friction. Maybe your motors have, as they wear, they change in their power, and then this will help to correct for all of that. So your robot will still do the same thing despite minor changes that occur from round to round or competition to competition.